this. Okay. All right. All right, chapter 14 review. So I'm going to do a couple things, hit the big ideas. And the first thing I'm going to look at is Euler's theorem, which is one of the first things we learned in this chapter, okay? Euler's theorem, which applies to connected graphs only. Okay. Euler's theorem enables me to tell if there's an Euler path or an Euler circuit. Okay. And do you guys kind of remember how we do this? Remember, if it has Euler's theorem says that if we have exactly two odd vertices, you guys remember what that means? If we have exactly two odd vertices, you can pipe up, turn your volume on, or write it in the chat, whatever you want. What did Euler's theorem tell us if we have exactly two odd vertices, odd degree vertices? No one remembers? That means it has at least one Euler path and no Euler circuit. Okay? So one way I can tell is if there's an Euler path and no Euler circuit is I look at the degrees of all the vertices, and if there's exactly two odd vertices, then I have at least one Euler path and no Euler circuit. Okay? And any of the Euler paths that I find, if I actually wanted to find an Euler path, remember, then I have to start at one of the odd vertices. I would start at one of the two odd vertices. Does anyone remember what an Euler path is and an Euler circuit? Just remembering, trying to remind ourselves of that while I'm writing this. Well, I'll just tell you then. An Euler path is a path that hits every edge without retracing any edges. And an Euler circuit is a path that hits every edge without retracing any and starts and begins at the same vertex. Okay, that's the Euler's theorem, or the path and Euler circuit. Rather. So Euler's theorem also says if I have no odd vertices, or all even, okay, then I have an Euler circuit somewhere. There's an Euler circuit somewhere. And if I have more than two odd vertices, then I have no Euler path or circuit. Okay, so that's just a reminder of Euler's theorem. All right, so let's do an example here. I'm going to make up a random graph. So if I go ahead and make up a graph, so this is my graph, A, B, C, D, E, F, G, H. So I want you guys to figure out, using Euler's theorem, does this have an Euler path, an Euler circuit, or neither? So take a minute to try to figure that out. Okay, let's try this. No one's trying to answer, so I don't know what's going on out there. So let's look at whether or not the vertices are odd or even. Well, it looks like A has even is even because there's two vertices coming out of it. So this is even. Looks like C is even because there's two coming out of it. Looks like B is even because there's two coming out of B, two edges coming out of B. So there's even degree. D looks like it's odd, right? 1, 2, 3 coming out of D. E looks like it's odd, 1, 2, and then the circular 1, 3. The loop is a third one, so E is odd. F looks like it's 1, 2, 3 is odd. And then G and H are both even. They both have two coming out of it. So since there were three odds, that means that there, according to Euler's theorem, is no Euler path or circuit. Make sense? Go back to the theorem. More than two odd vertices is no Euler path or circuit. Make sense? Okay. So that one has no Euler path or circuit. So now to find, let's do Fleury's algorithm next. Remember, we're just kind of overviewing these. I'm only going to do I'm going to overview these. So Fleury's algorithm. Fleury's algorithm helps us to find an Euler path or circuit. Okay, that's what Euler's path helps us to do. Once we know there is one from Euler's theorem, it's an algorithm that helps us to actually find one. So one, if I have two odd vertices, I'm going to have a path. Okay. I would start at an odd vertice, either at an odd vertex, either one of the two that I have. All right. And then trace through the graph avoiding any bridge. Unless you have to cross it. Okay, so if you have two odd vertices and you're doing an Euler path, you start in an odd vertex, then trace through the graph, avoiding any bridge unless you have to cross it. Okay. If you have all even vertices, okay, that means you're going to have an Euler circuit. Start anywhere. You can start at any point. Then trace through, avoiding a bridge. Unless you have to. Okay. So basically, Fleury's algorithm says just start if it's all odd vertices and you have an Euler path. Start at one of the odd vertices and trace through, avoiding bridges. All even vertices, trace through and avoid bridges. The only time you take a bridge is if it's your only choice left. If it's your only choice at a given juncture. Okay, let's do an example of this. Okay, so I'm going to make a graph here. So A, B, C, D, E, and F. Okay. So first of all, let's figure out if we have an Euler path or circuit. So let's look at all these individually. So looks like F has an odd degree because there's 3 coming out of it. 1, 2, 3. Looks like E has an even degree because there's 2 coming out of it. C has an odd degree. A has an even degree. B has an even degree. And D has 4 coming out of it. So it has an even degree. So this has 2 odds. So that means this is going to be an Euler path. Okay, this is an Euler path. Well, now that I have an Euler path, I'm going to take a look at, I'm going to start at one of the odds it says in Flory's algorithm. So I'm going to start, somebody throw out, you want me to start at F or at C? Anyone? Pick. Okay, let's start at F. Sounds good. All right. So if I start at F, and then I'm going to travel along, and remember how we did this last time? I recorded it here, and then as I went, I deleted so that I would know, whether or not I'm crossing a bridge or not, because you got to delete them as you go. If you remember with Flory's algorithm, I actually, at the last example, I deleted them as we went. So I could pick anyone randomly as long as it's not a bridge. Well, if I'm going from F, I could pick this one, or that one. None of them are a bridge, because if I delete any of those, I'm still have a connected graph. So what I'm going to do is I'm going to just pick the one to E first. I'm going to delete that one. Okay, so I went to E second. Now my only choice is to go to C. I'll delete that one. Now I've got 2 options. I can either go over to D or I can go down to A. Doesn't matter which I pick. Neither of them is a bridge. So I'm going to go to A. My only choice now is to go to D. That is a bridge. If you notice, if I eliminate D, that's a bridge because it left A by itself, but that's okay because it was my only choice. Okay, so I'm going to go to D. Now with D, I've got 3 options. I could either choose F, B, or C. I'm not going to choose C because that's a bridge, isn't it? And so out of my 3 choices, C is now a bridge. So I can't pick that one because it leaves C all by itself and I can't get back out of there. So I'm going to choose the one to F. Then my only choice now is the curved one down to B. My only choice now is D. And then my only choice left now is C. So that's an Euler path. There is more than one. I didn't have to choose that route. But what I did is I chose an Euler path. And I used Euler's theorem to first determine it had a path because it had 2 odd vertices. Okay, do you guys have any questions on that to start off with before we move on? That was section 14.1. That was section 14.2 rather, my bad. 14.1, guys, was just a review of 14.1 was just a review of, was just basically all the terminology of what a path is, what a circuit is, what a edge is, what a vertex is. That was all just terminology for the most part. Okay, so now we're going to go on to the next thing. Okay, we talked about Hamilton paths and circuits. And can anyone tell me what we talked about a little bit last time, what a Hamilton path is or circuit versus an Euler path? So Hamilton versus Euler. Paths and circuits. Whoops. What's the big idea in Hamilton versus Euler? Can anyone tell me that? Hamilton, Euler. Well, nobody wants to apparently. So Hamilton deals with hitting, every vertex. And Euler deals with hitting every edge. Okay, that's the big difference. So a Hamilton path hits every vertex once and only once. We only allow to hit once. An Euler path hits every edge once and only once. A Hamilton circuit hits every vertex once and only once, except that it starts and begins at the same vertex. So obviously it's going to hit that vertex twice, but every other vertex it'll hit only once. And an Euler path hits every edge once and only once and starts and begins at the same vertex. So there's some similarities, but one's talking about vertices and one is talking about edges. Okay, one talks about vertices and one talks about edges. All right. So now we're going to go through the nearest neighbor method. If you remember that, that's a big, difficult part of this. So when we have a weighted graph, the nearest, for weighted complete graphs. Okay. So this is a complete graph. And we're going to do an example and we're going to review how it works. Okay. So for the nearest neighbor method, take a simple example here where I create a complete graph like this. And I'll put some distances on here. And this diagonal going down. And that diagonal going across is 21, okay? So the nearest neighbor method, to review how we do it, is basically we're going to try to find the shortest. This is the traveling salesman problem. The nearest neighbor method is an approximation. Just keep that in mind. This is not exact. This doesn't give us the shortest travel route. It gives us an approximation. We generally want to use it when we have lots of vertices, when the brute force method is really hard. If I was using the brute force method, there's 6 different possible routes here starting at a given letter. So 6 possible routes. Starting at a given letter. When there's 4, there's 6 possible routes. And we'd have to do the brute force method. We'd have to actually find all the routes starting at, say, a letter B. We'd have to find 6 different routes. And then we'd have to check each one of them to see which one is the shortest. That is definitely going to be on the test, and it'll be in the homework. But I want to cover the nearest neighbor method because the nearest neighbor method gives us an approximation, which is what we normally use in the real world. We don't care about exactness in the real world. We just want something close. So we first start off with a starting point. So we're going to start in this problem. I'm going to say that we're going to start at C. Okay, we're going to start at C. So you have a starting point. So the nearest neighbor method says that we basically just keep choosing the smallest weight that comes out of that vertex, okay, that doesn't lead to a vertex that I've already visited. That's it. Because we're only trying to go to each city once. We're trying to get a Hamilton circuit that starts at C and ends at C, where we don't hit a vertex more than once, except for C, obviously, because we started and ended there. Okay. So let's and what we do is you do it in, I like to do it in red, or a squiggle line or whatever you want to use. So I have three choices: 15, 21, or 23. So I'll take the smallest one. Okay. So that'd be C to B. And I write below it 15. Okay. And then I have two choices from there, because I already went from B to C. So my two choices would be 31 or 14. 31 or 14. So I choose 14. So I go to A. So I'm adding up the tally as I go. Now I have a choice to either go 21 or 19. So I pick 19. That gets me to D. And then I have a choice to go 31 or 23. Well, I couldn't go to 31 anyway because I'd go to B, which I've already been to, that city. So I obviously take the 23. Gets me back to C. Okay, so this is my Hamilton circuit that gets me around on this weighted graph, and this is my distance. My distance is going to be, I'll add those up on the calculator quick. 15 plus 14 plus 19 plus 23, 71. My total distance. Okay, everybody clear on how that works? That's a little review of the nearest neighbor method, which there were some problems on that. All right, and then the last thing we'll talk about. Say that again. I don't understand what you mean. You said for Euler circuit. Did I say Euler circuit instead of Hamilton circuit? We do not use this method for an Euler circuit. We use it for a Hamilton circuit. I may have misspoke if I said Euler circuit. Yeah, no, this is just for a Hamilton circuit where we're trying to hit every vertex. We're not trying to hit every edge. An Euler circuit, we'd be trying to hit every edge. We didn't actually hit this edge or that edge, did we, in this drawing? So this is not an Euler circuit. This is a Hamilton circuit where we hit all the vertices, but not all the edges. Okay. All right. So let's go on to review just quickly what we did yesterday, the other day, where we look at trees and we look at spanning trees. Okay. Spanning tree is just a tree that it's a subgraph that contains all the connected graphs vertices, is connected, and contains no circuits. So basically, if I create a spanning tree for something, let's take a simple example. I'm just going to do an example for this one. Okay, so if this is my, I'm not going to put the letters on it because it doesn't really matter to see the letters to do this problem. So, but if I wanted to create a spanning tree for that graph right there, okay, I just need to basically find a subgraph of that graph. What a subgraph is just some conglomeration of vertices and edges that hits all of the vertices, but doesn't have any circuits and is still connected. So this is obviously connected, right? It has some circuits in it right now, right? Like for example, this is a circuit right here, right around that. So I need to create a subgraph of this that doesn't have that situation. So I might go something like this. And that looks like a tree, doesn't it? Because it is definitely, if I redraw it down here, if I redraw that, that is definitely hits every vertice, okay? And it is connected and it has no circuits, okay? So that is a spanning tree for that graph. It hits every vertex. Okay, that's not the only one, by the way. I could do a different one. I could go like this. That's another one. So there's not just one spanning tree, okay? There's not just one spanning tree for any of these. So the spanning part, guys, the spanning part means it's every vertex. The tree part means that it needs to be a tree. Okay? Hits every vertex and needs to be a tree. So that's what the spanning part means, that it hits every vertex. Okay, so that's something we did. Now we talked about, we apply this to a weighted graph. Okay. Kruskal's algorithm for a weighted graph. Basically, the big idea here is we're trying to find the minimally weighted spanning tree. For a graph. We're trying to find the minimally weighted spanning tree for a graph. Okay? So let's do one of these and just review again how we did this. So I'm going to create a big picture here. Make it as large as I can so it's easy to work with. Go here, here, whoops, here, here, and there. And then I got to connect all the other ones because it has to be a complete graph. Okay, so I got to put all the distances on here. This is 24, 22. This one across is 28. This one going down here, I'm going to call 35. This one going here, I'm going to call 23. This one going across here, I'm going to call a 31. And then this one down here is 14, 26, 12. I think I got them all except for this one right up here, which I'll call 21. I got them all now, just making sure I got them all. I do. Okay. So Kruskal's algorithm says basically the gist of it is that I pick the smallest weight in the graph if there's a tie, pick one at random, mark it in red, and then keep finding the next smallest edge, mark it in red, next smallest, mark it in red. And the only thing you got to avoid is what? Does anyone remember what I'm trying to avoid when I select my edges? So the big idea in Kruskal's algorithm is to avoid making a what? Circuit, right? So I basically just pick the smallest one, or in the event of a tie, pick randomly, and I'm trying to avoid a circuit. Okay, so let's do that. Let's pick the smallest one. Well, it looks like the smallest one is 12. Pick that one. And so that would be, let's write that down, 12. Okay. Then the next smallest one looks like it's 14. So far, no circuit. Fair enough. And we're going to keep going till we hit every vertex. Okay. Because when we're making a spanning tree, we want to hit every vertex. And then the next smallest one looks like it is 21. That doesn't make any circuits. And then 22 looks next. Next. And I believe that I have hit every vertex, haven't I? I've hit, there's only so many of them. I've hit this one, I've hit that one, I've hit this one, I've hit that one, and I've hit that one. So I'm done. That is a spanning tree. Okay. So now I just simply add those up, and my total distance is 12 plus 14 plus 21 plus 22, which I could do in my head, but I'm too lazy to do it right now. That'd be 69. That's the total weight. Any questions on that? Okay. Well, that is it for my overview of all the big algorithms and definitions and ideas. Okay, guys, we hit pretty much all the big algorithms in the chapter. In theory, you know, if you can handle all that, you can probably do most of the problems in the book and on the test. But I do have the chapter 14 review you should work through, because it's got a lot of problems along these